40, and we start our second session, which is focused on astronomy. So this session will be taken by Professor Annapurni Subramaniam. She is Director and Senior Professor at the Indian Institute of Astrophysics. It's interesting that, in the first session we had Professor Kaur, who spoke about the importance of mentorship. We had the second session, which was presented by Sai Geeta, who acknowledged Dr. Annapurni as her mentor. So now we will have the mentor speaking. So briefly about Professor Annapurni. She is a scientist and postdoctoral fellow at the Indian Institute of Astrophysics. Her major field of research is star clusters, open and globular, star formation and pre-MS stars, galactic structure, stellar population. And some of the projects that she is currently working on are emission star lines and star clusters, star formation history of young stars, halo of small okay, sorry about that. Magellanic clouds. Okay, so I'll leave the rest to her, who's the expert. Thank you, Dr. Prof. Should you please join us on the stage?
Good morning. Thanks to the organizers for inviting me here to talk about what I'm passionate about. And I hope you can see the slides. There's a lot of light here, but I'll try to show some of the night sky pictures, which are normally seen best with a darker background, but it's quite a bit of light here. So I was kind of giving kind of a few topics which I can talk about. In the meantime, I just wanted to talk to you about the picture which I have displayed on the first, in this itself. So this is, maybe it is a bit better. Do you think it's better? Okay. Yeah, thanks. So this is a picture of interacting set of galaxy called Stephan's Quintet. It's 4 galaxies interacting together. Now, what's the beauty of it is because the night sky, you can see a lot of stars, but you can't see galaxies as such. But you need telescopes to see the galaxies in a resolved way. Like what, in the introduction it was mentioned about Magellanic clouds. That's actually, these are 2 galaxies which are in our backyard, rather closer to us, which are called Magellanic clouds because Magellan used them for navigation. And they appear like clouds, but they're not clouds. They're like a patchy thing on the sky. You actually see them all the time in the southern sky, basically. And that's used for navigation. And you don't know, he didn't know what it was, but then you use the telescopes to look at them. They turn out to be a lot of individual stars. So they're galaxies, actually. So these galaxies, you need to look at them in grand detail. You need telescopes. Telescopes are made using grand engineering requirements and, various, it's a big machines. Now, what's important about them is that this picture is actually a false color image. So you do come across a lot of pictures in astronomy, fantastic pictures you see from various missions. Some of them are real images in RGB, like, real RGB, red, blue, and green. But in many cases, you do have to depict what you have seen in other wavelengths than the wavelengths which I can perceive. So in this case, the yellow image is taken from the JWST, the James Webb Space Telescope. It's actually in infrared. It's looking at the sky in the infrared. So if you want to depict the image which is just seen in infrared so that our eye can see, you have to give it a false color. And so what is true about this is the intensity of the wavelength in which it is observing and not the color. So the color is actually a false thing, but the intensity, what you have observed, is the correct thing. So yellow is the infrared light which is captured. So what it is supposed to capture is the cooler part, which is from stars which are not very hot, and also material which is cooler material. Now you can also see the violet or the blue color image out there, and that is coming from our own space observatory, which is this AstroSat. So the UV imaging, ultraviolet imaging telescope in AstroSat has captured the blue light from it. Now that blue light depicts the ultraviolet part of it. Now, ultraviolet also I cannot show you in a normal color because I can't see it. So I have to use a color which is like a blue, which is kind of tending towards ultraviolet, but what the intensity we have captured is true. So looking at the intensity distribution across these things, you can clearly see that the yellow light, which is depicting the cooler material, is not co-spatial with the material which is emitting in the ultraviolet, which is supposedly hot. Which basically tells you that if you want to study these kind of things, which are physical processes which are happening there, you cannot isolate yourself to one wavelength. You have to actually sample in all the wavelengths together to get a full picture of the physical processes which are going on there. So how is the ultraviolet light, which is distinct from the other emission, will tell us that there's a distinct process which is going on, which is resulting in the ultraviolet emissions. So previously, if you have only one wavelength to sample it, you assume that all the emissions are coming from the same region, and you attribute some other physical process to it. So astronomy nowadays is done using multi-wavelength, and it requires instruments placed on the surface of the Earth as well as in the space. So both ground and space are required to make such images and then derive physics out of it. So that is the idea behind the first slide. And this is published from Prajwal Joseph 2022. It is a combination of the James Webb and the UV imaging telescope. I can go to the next slide. Yeah, so ground-based astronomy is based from observatories on the ground, which is basically located at remote places where you have less light pollution. And this is the picture of the Vainabapu Observatory, and this is near Vellore. It is only 200 kilometers from here. You're welcome to go and see the place. It's a wonderful experience to see telescopes. And so since the time of Galileo, once we started looking up at the sky using, I did press it, yeah, did press it, didn't go. Yeah. So we have been operating the telescopes. Now the telescope, this will not work. So the one on the left side is the 1 meter telescope, which is actually 50 years old. So it was established in the early 1960s. Towards the end, it took some time to establish the observatory and set it up, etc. It completed 50 years. In the last year, we celebrated it. And the important thing is, 50 years ago, the telescope had different technology. The detector were photographic plates. So even though we create these big telescopes, which are very big, the technology changes. It actually witnesses the technology change through the time. So now the detectors we use are semiconductor devices, CCDs, and even the drives change, even the encoders change. So it's an engineering process which also have our engineering teams also understand what was the technology with which it was created, then modernize it through the time. So it's a very long investment in terms of technology, and it also grows with the technology, changes with the technology. Where else do we have observatories? This is another example where, I don't know whether you're able to see the entire thing. This is a picture taken from, full sky picture taken from our observatory in Ladakh, which is in Hanle. This is the Indian Astronomical Observatory, operated by us. This is set up around 2000, and we are almost there with the 25 years of operation. On the right side, you can see the 2 meter telescope, Himalayan Chandra telescope, and this is a night sky astrophotography done by our engineer in charge, Dorji Angchuk. So you can see the night sky full of stars in this place. Here now, you can't even see sun because of pollution and light pollution as well as general pollution. And forget about stars. So this is one place where people get amazed that, are they actually the sky full of stars? That's a question people ask now. But I grew up in a place where I used to see a sky full of stars. It used to exist, but now it doesn't exist. Yeah. So this is a picture, but this is a astrophotography picture. So you because of technology, you can take pictures, you can process it, and make wonderful pictures of the sky. So this is an example of that. Here it is a time-lapse image where you can see this Geminids meteor shower. So this meteor shower, we had taken time lapses throughout the night. So these are taken from DSLR cameras. They are not taken through telescopes. So I just want to make it clear. So on the time lapse, you can actually see that the meteor shower originates from the Geminids actually. At one instance, you will not be able to make out, but you integrate the entire night, you can actually see that it's emanating from Gemini's meteor shower. But it is important to keep these, preserve these sites. So we're working with the UT Ladakh administration as well as the local community to preserve the sky, and the government has declared a 23-kilometer area around it as the dark sky reserve. We are putting instructions and implementing light control mechanisms so that it doesn't get polluted over the time scale. So what do we have? We have this. I've given 2 telescopes, which are kind of a big beast now. This is the 3.6-meter telescope in Nainital. So it is in Devasthal, operated by the institute in Nainital, Aries Institute in Nainital. And this is the bottom one is the 2.3-meter telescope in Kavalur. There are also a few more telescopes in the country which has come up in the last few years, but they're all under 4-meter kind of stuff. Now, even the 4-meter kind of a telescope is very big. And so now if you want to look at where do you want to keep them, you want to keep them on the ground or you want to keep them in the sky, in the space. Now, these are very big, very big machines. Lifting them up, operating them is very difficult. But there are certain requirements, as I mentioned, certain wavelengths don't penetrate through the atmosphere and come down. So then you need to put them in the up. So these are the 2 important things. One is that the wavelengths which is seen, you can see the visible spectrum. So the transmission of the atmosphere happens then, but anything shorter than about UV like 340 nanometer, atmosphere stops because it absorbs them, and that is actually helping the life to thrive as well. So high energy photons don't come, but that doesn't mean the objects out there, including the sun, is not emitting in these photons. So the only thing is to have a mechanism to sense these, make a device and put it above it. So that's where you need the requirement of a space telescope. You also need a space telescope for observations of the infrared because the atmosphere water content absorbs it. There are sites which are like the Hanle, which is actually a high altitude desert. It is at an altitude of 4,500 meters above sea level. So it's a high altitude, it's also desert. So you can actually reduce the absorption content of the atmosphere from there. So these are observatories which are identified. They're not so many there in the world, but there are only a few of them. That's where telescopes are kept. And the turbulence also reduces the sharpness of the image you get. So if you have a less number of photons you're collecting, your profile has to be very sharp. Then only you can detect it. But if it is turbulent, the profile kinds of spreads, which is part of the noise itself. So you can't detect it, even though you are capturing the photons. So the sharpness is decided by the stability of the atmosphere. So again, the remote locations where the lamina airflow is available, so these are taken. If you want more sharpness, again, you have to lift it up above the atmosphere. Next slide, please. So keeping this in mind, the Great Observatories program of the US has put in the Compton, Chandra, the Hubble Space Telescope, etc. And the other one is am I blocking the view? I just don't want to, I'm aware of it. I didn't want to block the view of this slide because I know that this is standing in the middle. I'm aware, yeah. So this is the AstroSat where India launched in 2015. And the 2 yellow tubes I said is the UV imaging telescope, of which I was working as a calibration scientist on that. So these multi-wavelength observations are very important, as I mentioned, because just one wavelength data is not enough to tell you what the physical process is going on in there. So why do we need them? Because the telescope's bigger and which can actually take sharper images, can see look-back time because you can actually detect fainter objects and which are also in the, further back in the time. So you can actually see, look back, how was the universe when it began kind of thing. So how far have we reached with the James Webb? We have actually reached only about, if you think the universe is about 12 to 13 billion years old, we have been able to look back at the first 500 million years. So that much we have been able to see, but we still are trying to figure out how closer we can get to understand how the early universe was. That is the scope as such. So this is the Webb telescope which I was talking to you about. The most important thing being, I just want to give a minute on saying how do we make big telescopes. If you want to look at it, if you say telescope, optical telescope, you all think of a tube, right? So that's the first thing that comes to your mind. And why is a tube? Because you have a lens, normally a lens, and then the light comes in and the image is formed on the other side, right? So then you somehow take the image out or you look through an eyepiece to look at it. That's how it works. But what happens when you make it bigger? You can't use lens because lens becomes very thick and big to bulky to handle, etc. You convert into mirror. So mirror means you get the light, the mirror reflects it back to the same side, and then you put a 45-degree mirror to reflect it out, so you can put an eyepiece and see it. So that becomes a small, like 1 meter telescope is like that, where you have to have a focus at the center, you bring it down or bring it on the side, it's up to you. So you design the telescope like that. So mirror-based telescopes can become bigger. Now how big can that get? We know that you have to create a blank, glass blank, then polish it, then coat it, because just simple glass will not reflect. You have to coat it with a metallic coating. Normally it's a metallic coating of aluminum, but here it is different. So that coating, and then it reflects. Now how all these are engineering processes: deposition of a thin film, creating a blank, polishing it, measuring it, etc., etc., and supporting it. It's not like you keep it like this, it tilts like this. So you have to support it and operate it. So you cannot go beyond 8 meters because it becomes too risky, because the glass blank is too big. It can break. And you have the coating chamber of this big. You have to coat the entire surface evenly. So that becomes too much of engineering risk. What do? You break the mirrors into smaller pieces and then make it into multiple mirror segments and then make it into a bigger one. Engineering challenge again, because you have to align everything, and the entire broken set of mirrors, multiple mirrors, have to act like a single mirror. You can't claim, you have to actually enforce it so that you get a sharper image. Now this one is such a multi-mirror telescope up in space. So this is the first multi-mirror telescope in space. This is an engineering marvel, because you not only created it and enforced it that it works as a single surface in the ground, you deployed it in space 1.5 million kilometers away and works. The only deployable thing was the secondary, which is actually at the end, because it's a long tube. So actually it was folded, and after reaching the orbit, it was extended out. So to detect such faint sources, or in order to explore the first a few million years of our universe, you need such engineering marvel up in the sky. So it's a truly engineering-driven science. Otherwise, you will not be able to gather the data or do something. So a huge engineering process is behind astronomy to do astronomy. So that is the state of affairs now. Now, where do you keep these huge, humongous telescopes? We have 3 options. One is this low Earth orbit, which probably you might have already aware of. This is where the International Space Station is. This is generally about 300 to 600 kilometers, and AstroSat is also there. Typically, the orbit is like once in 90 minutes, it completes the orbit. So you will be able to command and bring the data back, etc. Low Earth orbit is also very easy, because to maintain International Space Station, you have to supply cargo. You have to keep supplying material, bring it down, send people, get them down, etc., etc. So this becomes much easier. If you are further, you have to fill the fuel, etc. Right? The next one is the sun synchronous orbit, where sun is on the one side. You should also remember that the power for all this has to come from sun. The solar panels have to see the sun. That's how the power is generated. If you design an orbit where it doesn't see the sun, then your entire system will be drained of the power. So that's not acceptable. So orbits are designed by various constraints. So this is the sun synchronous orbit, where normally the Earth observation, you put a satellite to see this Earth, is operated. The next one is the Lagrange points. That's very important, because the Aditya L1 mission, which went to the L1 point. L1 point is nothing but 2 objects which are of gravitationally attracting. You connect a line between it. One point, you will have equal attraction between the 2. So it's kind of a semi-stable point. It's a null point. There is nothing, no object out there. So if you want to put an orbit around it, you put an orbit like this. So this is a connecting line, have a plane perpendicular to it, and then orbit like this. Now remember, Earth is not stationary. Earth is going around the sun. So this L1 point will also go around. So you are actually tracing an inner orbit. So that's why you have various experiments can be conducted there. Now coming to James Webb, you can have one point in between. Symmetrically, you can have a point on the other side. Now, the Webb telescope is on the other side. It wants to see the night sky. But the solar panels will be facing on the sun so that it can get charged. So these are the different types of orbits where generally the missions are kept. So this is the last mile connectivity. You have designed the instrument, you have put it up in space, you're getting the data, but a few people who are actually design the experiment will get the data, but now more people can do work with it, right? So data, how do you disseminate the data? Unless you curate the data, you cannot disseminate. So just want to take a step back and explain that astronomy actually used to generate a lot of data. Even in when I did my PhD in early 1990s, neural network was available for astronomy data, because data has to be, to be used, you need to be in standard format. So there was a consortium called Virtual Observatory Consortium. It was funded. Virtual Observatory, what it did was it actually gave guidelines for data, how it should be stored from any mission, so that across the world people can use it. So that standard established structured data with metadata available so that you can use it, you can actually train tools on it. So astronomy actually led in the forefront of the data mining and also the machine learning concepts. So here you have to disseminate the data. So these kind of portals are available now with the NASA. Not only data is available, they also give you space to park the data, so that you don't see, the question is, the students will ask, okay, I have 1 TB of data, I have to run the 1 TB of data, my laptop will not take it. Where will I place the entire thing to run it? Now you also give space in cloud so that you can park the data, put your code, analyze it, only download your final results to your laptop. So this way, actually, the data democratization has happened in astronomy, and not only that, many people are able to do research. And people who are not well known with the astronomy are able to put very foundational papers on this based on data analysis, so which was not possible earlier. Now, from our ISRO side, also we have websites which disseminate data from AstroSat. There's one more slide, next slide. So you can actually see the data archive and dissemination page. You can actually log in and find out what data is available, download it, and the previous web page had the tools and techniques, how to use them. So unless and until we do this, we keep getting the questions of, okay, the government has made so much of public money invested in your experiment. How did you use it? How did you disseminate to people? So these are the systems, back-end systems which you need, which not be actually visible upfront, but you need these to actually disseminate and make it more usable. Otherwise, it becomes very difficult to sustain the investment in large projects. So going back, where did we start? Astronomy was a very important topic in earlier days. So our texts on Surya Siddhanta, and these are the many authors who have written many texts in ancient astronomy. So in India also, astronomy was a very important topic. And mathematics, a lot of mathematics India has contributed to understanding how to do this, etc. Why did we do it? Because we have to calculate the positions of the planets. We also have to calculate the months, and how is the lunar month done, how is the solar month done, etc., etc. Because our calendar system was based on these. And also we have to predict eclipses. So these were the computations which was done. So astronomy was important as a life skill, because if you get lost, you need to know your direction to go. So the stars and the constellations were taught upfront, without which you cannot survive. So similarly, the sea voyagers had to understand astronomy. It was one important topic for them. But now we have forgotten it. So can you go to the next slide? So do we need astronomy now? Is it relevant to our life? So not clear, because we know that there's GPS there, and GPS is actually looking up and giving us coordinates and positioning. Especially previously, if you don't know how to know your longitude. You need to look at the stars and devise a mechanism to understand your longitude. Now you don't need anything. Your GPS tells you everything. Now, so the thing is done, astronomy relevance is gone? Not really, because GPS satellites are on the move. Earth is also on the move. So if they can give you relative coordinates, but if absolute coordinates, you still need constant framework. Even for interplanetary explanation, you need constant framework. That's given by quasars. So these are actually quite distant. So for us, in the moving framework, that's kind of, you can take them as constant, non-movable frame, and that is how we use it. So it is still relevant. One more important thing is the elements. So we know that the elements are classified based on the periodic table. Now, where did the elements form actually? we very well know that we cannot manufacture these elements on the surface of the Earth because it requires high temperature and fusion, etc., etc. Now, where did these elements get formed? So it is formed in stars. So these are classified in terms of which elements can be formed in stars. And certain elements can be formed in low mass stars, stars which are less mass, and certain elements are formed only in high mass stars. So if you look at the chemistry of, you can go to the next slide, this is the structure we understand that the stars, big stars have, that you have layers of different elements, and the center is the iron core, and it actually collapses under its own gravity. That is when you have the supernova explosion happens. And when that happens, the outer layers with all these different elements get ejected. And that's when it pollutes the system. Now, this is not the same thing for stars like the sun or slightly little more massive than the sun. This is very massive stars. So chemistry differs, and they also produce different isotopes. The reason being, all these nuclear reactions produce a lot of neutrons. So neutrons can be plenty at certain areas where you can actually have C12, C13, etc., etc. So they also end up in producing isotopes. Now you can tell me that, okay, you're giving me stories. How the heck do I know? Do you have experimental evidence that actually the nuclear reaction goes on in the sun? So the evidence came from tracking something called neutrinos. So the neutrinos are produced as a nuclear reaction. It immediately leaves, and it doesn't interact with matter. So you can actually trace them immediately. So experiments like Kamiokande actually have traced it. So we have a valid explanation, direct evidence for nuclear reactions going on there. So that is the reason we know that with the atomic number, this is the present day solar system configuration as a function of atomic mass and atomic number. So, where are we? So what do we do as Indian Institute of Astrophysics? We also hold a heritage because it started off with an observatory in Chennai, and it was a Madras observatory, and it moved to Kodaikanal in 1899. And this observatory is functional, still collecting data, and this observatory is celebrating 125 years this year. So it's one of the very unique observatories in India where it is 125 years still functioning. It's not like a museum. We have a museum, of course, but it's still functioning observatory. And we moved to Bangalore in 1971. We have completed 50 years. So going to the next slide, these are some of the, so these are the different centers. We have centers across India. So this is our ground-based centers. And we have a center in Hosakote where we integrate our space payloads. And we also have set up a segment polishing facility for the 30-meter telescope project. And so we have ground-based multi-wavelength presence and space presence. So these are the kind of activities we do, and some pictures are on the next slide. So these are our pictures. Anybody wanting to visit these observatories, please get in touch with our outreach. You can do that. Just want to give one or two explanations on this Aditya mission, which also came to the news because it was after Chandrayaan, so the mission to the moon. This is not mission to the sun, it is a mission to study the sun, because you can't reach closer to the sun. It's only going to 1.5 million kilometers, and in fact the distance to the sun is 150 million. So it's only 1% distance you are going. But the importance is that we want to study the flares and the emissions, coronal mass ejections, and the space weather. Now you see that you have been living with the sun for a very long time. Why do you want to study it now? Why is it so relevant now, right? So the point is, you can go to the next slide. The Kodaikanal Observatory, established in 1899, started observing the sun from 1900 onwards. Now, as I said, 100 years ago, the technology was photographic plate, but the thing is, people had preserved the data extremely well. So we have digitized, calibrated the data, and made it available. So much of data is already available, and many people are all working on AI, ML, not on the generative AI, but ML on it, and then you can actually see the cycles of the sun. The sun goes through 11-year-old periods. Sometimes the sun is very active, you can see sunspots. Sometimes the sun is quiet, there's no sunspots. Now, the time when the sun is active is also not the same during these cycles. You can see that some peaks are very big, some peaks are low. So the thing is, can we predict when sun can be very active and flares are coming? Now, why do we bother about flares now? Because in a flare, it emits a lot of charged particles. And we have increasing space asset now. So these space assets can get corrupted, or the electronics on board can get actually destroyed by these charged particles. You have to protect them. So in general, if there is an advanced warning of the solar storm, you actually powered it down or put it in a safe position. Otherwise, you can't go and repair it. It's impossible. So that is very important. So that is what is going on to happen. And another next slide is that the corona of this coronagraph which we developed, one of the main instruments is to study the corona of the sun. You can also see why corona important. Sun is the most the disk is the bright one. Why are you chasing the corona instead of the bright thing? The corona is actually important because only it's seen during total solar eclipse. Because you have to block the brightest part to see the faintest part. Now, the corona studies which happen in India during the total solar eclipse, I think it is in 1858, in Guntur total solar eclipse, they measure the spectrum of the, obtain the spectrum of the corona. They had a line which they didn't know what it was. Later, it was identified as the helium. So, helium to do with helio. So, the sun, we know that the corona is a 1,000,000 degree temperature. Now, how do we trace a 1,000,000 degree gas? So, you have to identify an atom which is ionized and trace that spectral line. So, if you look at it, calcium and all that will be completely ionized by this temperature. So, you can only have iron. So, you can see the next slide where iron which is actually removed, the 12 electrons outside is removed. So, you need so much of energy to remove much of the electrons. So, it's actually looking into the atomic and the transitions to clearly identify what it is. So, it's true physics which is actually carried out in understanding the corona of the sun. So, this is an instrument. This is very complex because in order to identify each and every line and making the coronagraph, it's a very complex instrument which is flying up in space. And this is some of the pictures. So, this facility is in our Hosokote campus. And this is the instrument, the mirrors and all that. So, these are systems because space instruments are very special because you need to make sure that the design and everything is very nicely tested before you launch it because it becomes difficult to repair it after launch. So another point just before stopping to focus on the engineering which goes behind astronomy is this 30-meter telescope project which India has been partner as one of the mega science components. This is a 1,300 crore project. So there are several things. So this is a 30-meter telescope. So how do you make a 30-meter surface? It becomes very difficult, right? So 492 segments, 492 segments of 1.5 meter size. So you have to make it, put it together and hold it and steer it. So these are all completely engineering challenges. So what are India doing it? India is polishing about 100 segments and providing all the support for 492 segments and spares. So this is the L&T is already qualified for it and it's been a 5-year qualification process and we have actually working with about 70 industries in the country to actually make products. So the next one, so these are the deliverables which are going from here, the segments and then the segment support assembly. This is the electronics, sensors, actuators and the science instruments and the software as such. So these are all, we were working for the last 10 years on it. We are all ready with all the qualifications. So we are ready for production process. So these are the teams involved and the polishing is a very complex process. In fact, the polishing, traditional polishing will take 1 mirror 1 year. So now we are going to a different technology, which is called stress mirror polishing technology, which you can actually complete in 2 weeks. So it's an accelerated process, but very complex process. So that is what we are trying to do. So these are some of the other important projects which we want to undertake in the next 10 years or so. So many of them are the annual, but all are engineering driven because we have a large engineering team also to support us, but the requirements come from astronomers. How do you design requirements come from astronomers, produced by engineering and industry, and then used by Science Park. I just want to show, I come from a musical family. My parents are musicians, and they're professional musicians. My father is a well-known singer, and my mother was a professor of music in Palakkad. And we have music right from morning to night at home. And my children are also trained in music. I am a violinist as well. Just wanted to, so I have performed in some this thing also. Just wanted to give you a piece of violin before I stop.
It was a fantastic presentation, ma'am. I was in surprise and wondering about the miracles and magics that do happen. Thanks for giving us this session. So the question I have is, has astrophysics discovered or alerted human beings in any disaster management? In the sense like has it helped in detecting any mishaps and
Yeah, so the question is about mishaps where astronomers can alert. So let me give you an example of what mishaps are possible as we know it. One is the flare from the sun where you can actually destroy the power grids or space things that do happen because we do have flare predictions and say that you also even get misinformation in your WhatsApp groups where switch off your mobile, power it off, etc. So it is rampant, but truly there are predictions. Second thing is you also would have heard of asteroids coming and particles coming and hitting the earth. So that's a real threat. It is actually, the probability is low, but we have to actually be aware of that. So there are many things where the large sky observations do track these things which are coming. And in fact, there was a mission which actually succeeded last year, going and hitting an asteroid to destroy it, to actually see whether you can actually turn its trajectories from coming and hitting the earth. So it's a DART mission, it's called DART mission. It actually crash landed a spacecraft on it to make it change its orbit. So you can say that this is a possible way to avert tragedy, but can you execute it? So this mission was actually demonstration of that.
Hello, ma'am. My question is more about. Can you hear me? Yeah. My question is more about. See, you spoke about NASA, publishing the freely available data, right? So that anybody can access. So, do we have similar thing in India, like especially the Institute of Astrophysics, which is also having similar thing? And that's one. The second another part of the question is, do you have any reach out programs to students as well as exclusively for girl students, so that they can reach out and then work on these things? So yeah,
I covered these in the talk. Probably I just went through very quickly. So there is a website I showed by ISRO where the AstroSat data is publicly available. You just need to create an account and do it, and then you actually have data available thing is there, like NASA. That is for AstroSat. The other missions should also have them, but I do not know. But Astronomy has the criteria and the guidelines are already there. So this is in the same guideline, it is there. And second thing is, for us, from our data, as the data which I showed from Kodaikanal, 100 years data, this is calibrated, digitized and publicly available. You can look at our website. Anybody can download it in various filters. So it's even separate as filters, years, everything you can download. So it's a freely available data. And third thing is about outreach. We have a very good outreach thing. Please do get in touch with them. We organize a lot of activities. In fact, this National Science Day, we had about 4,000, 5,000 people coming up to the center. Not only at this campus, but we also, in all the campuses, we have outreach. Even in Kavalur and Kodaikanal, etc. So please write to them and you can get information.
A wonderful talk. Learned a lot. I wanted to ask you, astrophysics and meteorology, do you work together in any probably climate change kind of concerns?
Not really, because we actually, IMD, Indian Meteorological Department, and Kodaikanal Observatory were together. It was together actually. We do have weather stations and all that part of it, but we are most bothered about things outside, so not within the ionosphere kind of a thing. But atmospheric research people do it. We don't have atmospheric research component. People used to look at ionosphere variations through certain observations, but right now we don't have groups working on that. But yeah, not really right now.
Yeah, thanks, Annapurni, for the great talk. So, you mentioned the periodic table and the chemistry. So, is there an active group looking at, meteorites and then the new elements that can be traced from them, or when we send out spacecrafts to explore the space?
Yeah, so astronomy used to be actually the, remote sensing kind of a thing. You get the photons, you analyze with spectroscopy, that is how the mineralogy was done. But now you have Hayabusa missions where they actually go and scooped out the material, brought it here and then analyzed. So astronomy is actually changing the pattern, but you can actually do a lab experiment with them. But also lab experiments to suggest where, you can do, PRL does experiments in these planetary sciences, and also experiments on cold atoms when you have cold environments like the outer space where the material hydrogen and other elements are available. What molecules can it produce? So can you create organic molecules, a chain of organic molecules which eventually can lead to bigger complex organic molecules, etc. So such kind of systems and experiments are very specialized, and the Physical Research Laboratory Ahmedabad has groups working on it. We don't have planetary sciences as of now as a division with us.
So, hi ma'am. So, NASA has discovered lots of habitable planets, exoplanets, just like our planet Earth. So, does Indian Institute of Astrophysics is also working in discovering exoplanets?
We do. So, let me correct you. The habitable planets are not found as such. Only a couple of them are suggested to be in the Goldilocks zone. No, probably they are habitable. So we have not found habitable planets as of yet. And there are efforts to discover. So let me put it in the perspective. 20 years ago, finding an exoplanet was in the news because you found one star to have a planet. But now, in the last missions like Kepler and all that, we know that most of the stars will have planets. Now, you may have to discover a star without a planet. That may be of more importance than why the star doesn't have a planet. Then the stars of planets has become a norm now. The discovery will be to find out what kind of a chemistry the planets have. So, Indian Institute of Astrophysics is involved in looking at algorithms which can actually refine and see how the detections are done, and we are also working on an instrument which will go up in Keck telescope to actually do the spectroscopy of finding the elemental abundances of these exoplanets. That effort is on. Probably in the next 1 or 2 years we'll have exclusive data on spectroscopy. Yeah.
So can you throw a little light on the two telescopes that you have in the Nainital region? In the Nainital region. The bigger one is coming up,
So Nainital Aries has two bigger telescopes. One is the 3.6 meter Devasal optical telescope. That's a single mirror which you can steer it any way, and then traditional telescope kind of a thing. Traditional telescope means you can steer it, you can actually put in instruments, take it, etc. But there's another one called the 4 meter liquid mirror telescope. So that is another one where you actually have a plate and you pour the liquid it's a liquid mirror, so it's actually mercury. So spin it in a certain RPM, so the surface stabilizes over a period of time, and then you can keep it rotating. So the surface, the meniscus acts like a reflecting surface, but it cannot steer. So you have to keep it stationary. You have the instrument on top hanging. It looks at the night up above, zenith. And when the earth rotates, the sky obviously changes. So you can actually trace them in it's a transit mode. So that is another telescope Aries has commissioned. But you also have to have precautions because it's mercury. So your vapors will be there. You have to be, all the security precautions, safety precautions are taken. So this is a very different kind of a telescope we have in Aries, yes.
Please put your hands together. Thank you, Professor, for taking us on a journey to see the stars today on a bright day.